Hi there, it's me, Rigo again here. So, topic of today, another video about how to assemble a cheap and fun electronics/embedded systems laboratory at home. In this video, you're gonna assemble a power supply. I'm not talking about a PC, PSU, a personal computer power supply unit. I'm not talking about that, get the green, connect to the black wire, then you put the boards and all that. I want something adjustable and, you have access to more power. And by the gods, let's not go to the ubiquitous yet super common, simple and not fun 7805 or 12 or whatever. Let's do something, more fun to build, yes, but adjustable and capable. So roll the intro. Hi there, sorry about the camera quality, I'm still assembling the new camera, so this is what you got for today. If you go to your favorite cheap market, online, you're gonna find many types of power supplies. You have benchtop or laboratory power supplies, really expensive and really good. You have laptop or, USB smartphone grade power supplies. Very compact, really useful to have around. Then you have computer PSUs, power supply units. Then, they have this really rigid form factor, but not the most practical, especially when you want to make a do-it-yourself project. They give you a lot of different voltages, but that's not fun. And then our champion today, called by many names, but you can find them by industrial, CCTV, LED strip, whatever, power supply units. If you look for switched mode power supply units, you'll probably find one of these. Modular. This one kind of has a problem, but I have many of those. This is one of the most powerful. Here you can see its inputs are not quite like ideal. You gotta manually switch between 110 and 220, but its output is 12 volts, 50 amps. Yes, this is a 600 watt power supply, and it goes really cheap, so you can buy one and have some fun. It's switched mode, it has a lot of protections and no active cooling, if you can consider this a great amount of cooling, but still. And then you probably ask yourself, Rigo, this guy's fixed. You have an adjustable pot here, so you can make a precise voltage, but hey, plus V, minus V, line and neutral, and that's it. Well, here comes the really interesting part of my project. You got a really powerful and really ubiquitous and cheap power supply, coupled with a really nice buck converter or a step-down converter. This is a DC-DC converter, a really cheap and simple step-down converter. It has adjustable outputs, and all you gotta do is get some voltage in, get some voltage out. DC-DC, beautiful. Get these parts and an extra, voltmeter and meter. It is again super cheap. I'm getting this really common PC fan from my scrap parts, and I'm gonna assemble this into a really powerful yet useful power supply that will become my main power supply in my laboratory. So, how do you choose the ratings for this guy? We start by the converter. What kind of converter you can get your hands on? I chose this guy here. It's only 300 watts, This is not the strongest one, but it can output from 1.2 to 40 volts. It's a huge range. Of course, if you put 40 volts in the here. So it has a great range that can adjust voltage and current, and 300 watts, really powerful. So this guy here can handle 300 watts, no more. So you need a power supply with more than 300 watts, right? And of course with the highest voltages possible, so our buck converter can step down to 1.2 and upwards. So for this, I chose a power supply that is 24 volts, 15 amps, so 360 watts. And here it is. Yeah, you probably notice where is the case. So I basically took this board out to verify if everything is alright, and I'm gonna test this before I actually assemble the rest of the project, because you know, the switched mode power supply here is the core of the project. I could get a 300 and something watts power supply with a higher voltage rating, but this one I had in my lab already, this one I had already, these guys I had already. I didn't need to buy anything here, and luckily I get the parts I wanted. And of course, before I continue with this project, I must reassure you that yes, I'm an engineer and technician, I'm qualified for this job. If you're not an adult or you're not trained and you try to do something that deals with main voltage and high current DC voltages, you can get yourself hurt or damage your property, so don't do that if you're not ready. If you do, it's not my responsibility, you are a grown up, you know, you assume your shit. So, the best buck I could get 300 watts, 1.2 to 40 volts. I could not get a higher voltage power supply, but this one I really tested and is completely unloaded. The capacitors are really sleepy. They are really relaxed right now, so it's safe to touch. This guy is at 360 watts, 24 volts, 15 amps. So things here are, you know, coming to a nice conclusion. Extra that, I bought some components, but you can salvage components from other boards. Basic things, you know. I'm gonna change these pots here for better potentiometers to get in the front plate of my power supply, so you can adjust limit current and voltage. You're gonna explore this board a little bit more right after the introduction of this project. So from the last item I had at home was this power resistor in an aluminum case, because I want a way to, you know, actually measure the current in order to, you know, actually see what is the maximum here. So I'm gonna put a really low loads but high power, and then use the ammeter in our display to check what is the value in here, because it's completely analog, so you need a way to visualize that. Then I got some female connectors, rubber pads, LEDs, fuses and alligator clips, some knobs and high current buttons, some potentiometers, a lot of wires, and the most important item, wood. This one is MDF. I don't know how you call this outside Brazil, but in Brazil it's MDF. I don't know, they stick wood together and wood becomes wood. I really don't know anything about wood, but this is easy to work, glue, screw stuff into it and assemble a equipment for the laboratory. So let's start by the PSU. So starting by the PSU, you know, the core, the heart of this project, it actually came into this aluminum case. I had to write things down in order to make it easier. As you can see, 110 or 220 volts, and the output 24 volts, 15 amps. And there's a little bit, you know, really cute fan inside this cooler, and pads and mica to isolate everything. You cannot see, this is transparent. Let me see if I can see. You may think this is a plastic, but actually mica, you know, is a crystal. It's a material to keep things galvanically isolated. My PSU could be opened by really simply, you know, this plate here was held in place by 2 screws, and this will come off. Then the board came off from removing these 4 screws, and then, as you can see here, with the board in place, you have the switch for 110 and 220 volts in here. Here you have 2 power MOSFETs and another one here. I don't know if they're power MOSFETs or watts, but you know, 3-pin power package. And you have these small aluminum tabs with screws to really force them, you know, in a really good contact to the case in order, you know, to dissipate as much heat as possible. But they are, in theory, electrically separated, you know, galvanically isolated, because you have the mic underneath and then these thermal pads in here and the screws. Nothing touches, you know, the metal from the component. So let's just observe this board here before moving on with testing the PSU. And of course, after testing the PSU, we can move on to the rest of the parts in order to assemble your power supply. So as you can see here, you have line and neutral input here, fuse, another protection device, NTC, then you have what I guess is possibly a filter with these guys here, and then you have a full bridge rectifier. Yes, that's the max amount of enthusiasm I can put in it, but if you know, you know. And everything looks alright, you know, everything looks fine in here. But when you come to this part of the circuit, things look, well, not great. Let me just tilt the board a little bit and you'll see what I'm talking about. Are you seeing this? This is the worst solder job. Look at this capacitor, completely bent. Look at this device here. It's bent. Look at these two right here. They are sideways, and this resistor is like, oh my god. So, before moving on, I will resolder some of the passive components here and these active components here, because they actually offer a risk in here, you know. They might touch something that they shouldn't, be too close to another components, I don't know. And the under part here is not that fantastic, by the way. The pins are way too long. Don't know if you guys can see that, but I mean, way longer than it should be. In this part of the board, everything looks nice. But again, in these small parts here, this is I'm sure this was soldered by hand because the work here was sloppy. So I'm gonna resolder some components and then trimming the pins, you know. And after that, I'm gonna test the PSU, see if it's, you know, actually working properly, not burning or exploding, and then we're gonna move on to the rest of the project. So I know you guys cannot see a lot of improvements, but the components are now properly soldered. And yeah, I know these resistors right here, there's no fixing for that. I'm sorry. There's no way I can fix that. But now this board offers less risk to itself and to me. So I'm gonna reassemble this, and then we're gonna, you know, really scarily gonna move on to testing, because this guy deals a lot of power and mains voltage. So let's assemble this and test, and may the gods have mercy on our souls. So here you have the power supply unit ready for testing. So let's hook up a simple setup. I'm gonna change the camera here. I'm gonna get some wires in here, verify that everything is safe, and then we're gonna proceed to test this one. So this is the setup I'm using for testing. You know, multimeter, we connect it to voltage. You can see some millivolts in there, and then we come with the plug, electric shock, 24 volts. It's working properly. We didn't damage anything, and it keeps its voltage, as you can see. So the module is working properly, and now we gotta find out the best way to hook up with the other components, mainly the buck regulator. If actually we can plug a switched mode power supply into a switched mode regulator. There are a lot of reactive components, you know, into this equation. You know, the switched mode power supply uses, you know, its reactive components to actually regulate the voltage, and then our buck converter also uses reactive components to regulate the voltage. So let's see if that, you know, this whole mess actually works out really fine. So now that I tested my power supply units, you know, the modular PSU, you can hear in the backgrounds, plus the fan that I'm using for the soldering iron, you know, for the fumes. So it's working and really stable. And here you have it, you know, the minus and plus wires coming from the PSU and my multimeters to the outputs. This LED here I'm gonna split it, especially because the camera cannot get it super bright right now. There are a lot of lights in here, but you can see the left potentiometer is the voltage control, so it can make it go higher, but especially, you know, most importantly, just get a grip in there. We can make it go super low. So you have a Mac controller running on 3.3? Well, this power supply might suit you. You see? So now that you have a buck module and a PSU, we hope that our loads will be, you know, purely resistive, or at least the least reactive we can make. This apparently will work. There's no loading here. I'm gonna test the load later, but apparently the regulation, everything, there's no oscillation, there's nothing, it's really stable. And now that we tested both modules here, I'm gonna show you in detail how I plan to make this benchtop power supply using a modular PSU and a buck module. Let's go! So, let's talk more about the buck converter. There's nothing to see basically here. You see the main coil. Come on, focus. So there's nothing much to talk about the buck module, but it's important for me to show you because basically you're gonna try to mod this one, you know? We're gonna make this work as our own with an interface to the user in the front panel. So these guys here, I'm gonna need a potentiometer to use in the panel. You can see here the caps from the output, the coil. One of these guys here, more specifically this one, is the actual converter, you know, the buck controller. This guy is a pair of power diodes. Here you have inputs and outputs, but the underside is actually more interesting. So here you have a dual op amp, no, 358. Here you have a voltage controller, 7805, you know, the classic one with heatsink pads. Here you have a MOSFET, and here you have the current sensing precision resistor, you know, the shunt. So this is basically the circuit that you have on the underside. This is clearly the control circuit. But how can you mod this if you can barely understand what's going on? And most importantly, how can we effectively design an on-off control that doesn't just plug and unplug the controller? You know, that you have inrush currents, you can have a load plugged into your power supply. That button or switch will take a lot of amps in and out every single time. So it's important to try to control this buck converter without plugging it on and off the main power supply. So let's see if we can find any documentation, shall we? Luckily for us, we have a documentation. And by luckily, I mean I am super lucky. I bought a Chinese module with German documentation. This is the best of both worlds. So this is the buck controller, XL4016. And this board comes with these specifications. You see the main points here, you know, the one that I find extremely important. It's the really low output voltage, but this big voltage range. Unfortunately, I'm gonna be use everything here because you're gonna have 24 volts as an input, so you're probably gonna have like 20 volts max. And the operating current range goes up to 8 amps. This is important because the display I bought, again, all my components here are actually old, you know, some of them are older than my lab. So my voltage and current display go up to 10 amp. So the fact that we have 8 amps as maximum is really great. And here you have, you know, basic control scheme. And the best part of this document, we have a complete circuit schematic right here. This is beautiful. So remember, I have two pots, one 10K pot in here, one 10K pot in here. We have the 7805 in here, the XL4016, and remember the power diodes here for the buck system. So without looking at the board, what can we actually understand from this, you know? So the unregulated input goes to the 7805 and directly to the XL4016. So you have a really regulated linearly low noise for the op amps and the raw inputs for our buck regulator or buck controller. Here you have the basic buck switching schematic. You know, you have a ground pin. Without looking at the documentation, you can already see that you have like the inductor and diode in 3 and the input in 5, so the internal MOSFET is probably switching between these two pins. and you have like inductor, diodes, and the caps. So this is basically the core of the buck controller. Here you have this current sensing resistor, you know, the shunt resistor, and that power MOSFET I told you about. So let's just clear everything here up. Let me try to separate this into blocks after reading the datasheet. So this is the datasheet for the XL4016, a really cheap buck controller. Here you have the pins, and pin 2 is feedback, and the rest we just got it really right. You don't actually need to get everything for the internal function blocks, but the most important thing here is you have the feedback voltage, you know, then you have a sum, I assume here, because this is comparator, and you have a stable level voltage being compared to a sawtooth or a triangular wave. You know what you get, right? You have PWM control here, so then you have a latch and a driver. So this is basically everything made for a basic PWM control loop. And I have a lot of typical applications here, you know, see the flywheel diode, inductor, cap, outputs, and the basic feedback. Luckily for us, we have a circuit suggestion that looks really close to what you have in the controller itself. The control board shows us a feedback loop with the diodes and a control voltage. See, this is the feedback pin. We have a feedback loop here. You can see here, you have these diodes getting the voltage from the outputs into pin 2, a diodes, and the circuit composed by the 358 op-amp. So let's just break the circuit in blocks, you know. This guy here is regulated 5 volts, right? So you can just ignore this, basically. This pin here is just 5 volts. This here, using a TL431, is just a really stable voltage reference. You know, that's it. This is a voltage reference coming right here. So you can assume this capacitor here is just for filtering. You have 100 kilo ohms here, 1 mega ohm here, really low voltage, so, you know, not disturb this voltage regulation. So this is basically a voltage reference, you know, in these pins 2 and 6 right here. And what are pins 3 and 5? Well, current sensing from the shunt. So this circuit here basically controls what is, I think it is, the set point for the current. And funnily enough, we have here the LEDs, you know, and the LEDs go for the MOSFETs. I showed you this in the board previously, right? So this op-amp right here is just controlling the LEDs. The one important op-amp here is this guy controlling this voltage from these diodes, just as we saw on the example. So now we know that controlling this voltage that goes to the diodes, we can control on and off this power regulator. So let me just review this with you one more time, you know. You have a voltage reference to feed in our op-amps. Then this voltage is divided, regulated, and divided again to use as a set point for this control loop. This control loop turns on and off the regulator depending on the current here that is sensed by this shunt resistor. One of the op-amps is just used for the LED. I assume one is red and one is green, and depending on the cycle we have for the regulation, it can show in the LED the load, you know, is going to maximum or minimum loads using just color. This is what I assume, I didn't test it yet. The other one controls the power regulator by turning the on and off as we saw in the datasheet. Then you have this voltage divider right here and the basic circuit for the buck controller. So this is not as complicated as you might think looking at the first time, right? And as you know, this is a shunt resistor using for current sensing that comes into this control loop. We know that the set point must be the set point of a current controller, not voltage. So this guy should be our voltage control potentiometer, right? Well, let's just test that up. Let's test that theory. Here you have our board, right? And you have, as you can see here, both the pots. Well, this one sees CV and CC, current control and control voltage. Let's just ignore that, right? As you can see right here, both of these pins are connected and this pin is separated. This guy has 3 separate pins in the PCB. So the PCB tells us that this guy here, this potentiometer right here, is only a variable resistor, you know, not a voltage divider. So looking at the schematic, who is this guy? This guy right here. And as we analyzed, this is a control loop for the current. This guy must be the voltage potentiometer. And just looking it up, as you can see, CV. Better make it this way. CV right there. So this is the voltage control, and this is the current control. And now we know the pots we must desolder and then resolder in a panel so the user can control both set points. So let me just explain this basic schematic I just drew here to, you know, show you what I had in mind. And this is the final version. You had some revisions in the way, but basically you have here connection to the AC main. You have a fuse, a switch, then goes to the AC part of the PSU here. This is a generic PSU. You can get any PSU you want. Then you have the output with just, you know, a minus and a plus. That's the basic configuration of any modular PSU. With this PSU, I will just get some cooling fans on, and an LED showing that, you know, my primary part of the circuit is on. Then for practical reasons, I just chose to not go for the soft on-off control. Then of course you need a secondary switch here to control if the buck is on or off. I have an LED to show if the buck is on or off. This is here is to more than 10 amps because the maximum current you can get out of this buck I think is 10 amps. And the maximum current from the ammeter is also 10 amps. So you have a secondary switch, it turns off the LED to show the user you have a buck on, the step down converter is on. Then the step down converter, you know, output goes to the connectors in the front. You have the ammeter, you have the voltmeter, but the voltmeter here needs the primary voltage 24 stable. Why? Because this guy here can go as low as 1.3 volts, and that just turned this guy off. So I needed, you know, some more stable voltage. I got the primary voltage here. The LED, this little guy here, shows the power it's been drawn, you know, the PWM cycle from the regulator. I chose not to, you know, externalize that to the panel because that'd be, you know, a lot of hustle. You know, I was already tired. You know, this video, I started recording this video April 4th. April 10, I started working a new job. Then as you noticed, I got a new box. I gave up on the wooden box and a new job. I was kind of in a hurry to just finish the project and move on to new videos. So yeah, no LED or soft on-off control. Sorry guys. Then you have the two potentiometers that go to the panel, and this is basically everything you need to make it work, my version. You can of course take off the LEDs and the secondary switch. You can just, you know, take off the fuses if you want. The PSU is protected, you know. And you can take off the cooling fan if you really want to. You can keep this project to a minimum with only the PSU, the buck converter, the display. You know, in order to use a multimeter all the time, you can have a display right there. And to test the maximum current, because the maximum current here is analog magnitude, you know, there's an analog value in this analog circuit right here. So you cannot externalize the maximum current. It's an analog setup. I got here a resistor to work as a shunt to test what is the maximum current allowed by the converter. So I have a button here, a power button by the way, you know, it handles a lot of current, and I press it and I can adjust the maximum current the circuit will operate without using the circuit as a shunt. This is really important. This resistor here, as I mentioned in post editing, I think this is 5 ohms but has some wire and buttons, so I think it's 5.5 to 6 ohms. I chose this value because I had an aluminum resistor at home, and if I'm not mistaken, the aluminum case is rated for 50 watts. So this is the basic schematic, but remember you can take a lot of things out. I just chose this because I wanted to ensure I had, you know, air circulating inside the box to keep things as cool as possible. I went 2 fuses to keep things under control, and a secondary switch to turn on and off the primary part of the circuit. But you can work without any of that, and just the basic stuff that I show you do, PSU, buck, and display. You don't even need a display, by the way, if you want to go like super cheap. So the idea of the product is to be simple, easy to manufacture, easy to do at home, and I think I kind of get it. But of course I had a lot of components and I bought some that were cheap in order to flare, fluff, color you want. So this is the basic schematics for the circuit. I'm not gonna show you like me assembling this, because honestly it's just poking holes into a box and painting and then fixating stuff using some hot glue. It's boring. You're not gonna learn anything fantastic here. The idea here is to show you that you can assemble a power supply for not too much money, kind of cheap, and it's really capable and really versatile. So there's that. There's your basic schematic. Let's go for the actually working prototype that worked wonderfully. Let's go. So before going forward, this is the box with the marks I had. This is the bottom. I had to fit this PSU here, and I wanted PSU to have separate air cooling. There's that, and then the sides and the 127/220 volts selector in there. You're gonna understand everything once I show you the next pictures. And then the proposed layout for the display, you can see the DC-DC converter on the background here. This is what I proposed to do, and I forgot to put the fuse in there. And internally, I chose, you have like some heat sinks in here and one in here on the side of the PSU. So I decided, well, if you can blow wind in here and then some wind can get on the cables here, then I can got DC-DC converter and the power resistor used to test the maximum current all in the path of the wind. That would be great, and it's actually what I end up doing. And this is the final result. As you can see, the proposed layout. I kind of did not plan anything, to be honest, so this button could be a little bit to the left, the tester could be a little bit to the right, but this is just a quick project I did to cut some wood and to prove my concept. So there you have it. Then you have, yeah, so professional, but the important thing is you have plenty of access to the voltage switch in here, which is 110 in my apartment, and this atrocity of holes, but the airflow is really, really great. AC adapter, fuse, primary switch. Then you have voltmeter, ammeter, primary LED indicator, secondary switch, secondary voltage indicator, the fuse, current adjustments, voltage adjustments, the connectors, and the button to test the current. So how does it work? Well, let's test it out. So still with the low quality images, I'm still trying to get my tripod and old camera to make better imaging, but this is gonna work. So I turn off the first switch and you can see LED lights up. Then I turn the secondary switch and you have the power supply. I can adjust voltage here. Let me just get 12, such a classic value. This display is lower than I would like to, but this is the cheapest module, so yeah. And now you can adjust current, but how can you adjust current with no loads? Well, you press the test button and suddenly you short with a power load and you can control, let's put 5 amps in here. And you see 5 amps stabilized, release, and you set, the voltage you want. This is a really good power supply right now for embedded, for robotics, for RC. Basically everything electronic related, you don't need like huge, tons of power. This guy is really, really good. And in the end, you don't get like tons of power because the buck regulator is kind of, not that powerful. But for the price involved on this guy, I can get a lot of power, This guy is really, really, really strong, really powerful. And I know I got a lot of things connected in here, but your power supply don't need this much complexity, In the end, all you need is a PSU and the DC-DC converter, and this guy showing you the details. And the potentiometers make it easier, but one of these guys, no tester, basically you don't need that. LEDs and coolers, it's, because I wanted to make this the safest as possible, but you don't need to. Your project can be way simpler than that, and you can use like soft on and off instead of this rugged switch. So yeah, I hope you guys learned something, and I know this project is not like the best looking project ever, but it works reliably, and to me that's what's important in my lab. Thanks for coming to my underground archives. I hope you liked this project, and see you on the next one. Bye bye.